In Unit 1, we have seen the nucleon-nucleon interaction starting from the low energies to the higher energies. In second unit, we have seen the differential models. And in the third unit, we are going to deal with the nuclear reactions. So let us see the alpha decay. We know that the nuclear forces are the short range forces and which are effective in the range of nearly 2 femtometers. Now suppose there are two nucleons and which are at a distance. Now suppose this is a proton, this is a neutron, and which are nearly at a distance of 2 femtometers from one another. Okay, so this nucleons could experience the strong nuclear force. Okay, so this distance may be also 2 femtometer. So this may be 2, this may be also 2. But suppose there are some another nucleons which are at the range of this again 2 femtometers. So here this is a very classical and a rough diagram. Actually we have already seen how the nucleons are arranged in the nuclear shell. Okay, this is not like a hard wall, this is not like classical entity, but still we are trying to estimate the nearly at what range the nucleus in the nucleus will not feel some the nuclear forces. So this we know from the quantum mechanics that the nucleon potential is there. So the nucleons attract one another up to the range of this 2 femtometer, or the nuclear forces are effective from 1.5 to 2 femtometers nearly. Okay, suppose there are the nucleons which are greater than this distance. Okay, so when this r is greater than say 4 femtometer or 5 femtometer, the nucleus becomes unstable, or you can say that at this range the coulombic force will start to play its role. Okay, so if suppose this is the nucleus and there are nucleons inside the nucleus. Okay, so if this is the case, actually they cannot come much closer than 0.5 femtometers. This also we have calculated in the first lecture. Suppose there are few nucleons in the nucleus, and these nucleons are attracting one another by the nuclear force, but there are some nucleons which cannot be attracted by the nuclear force, or there is an imbalance between and there, see, in the nucleus there is a nuclear force which tries to bind the nucleons together inside the nucleus. Along with this, there are some protons which are having the positive charges. Actually neutron is also having charge in the nuclear and particle physics. Like proton is made up of proton is made up of u and d cores, whereas neutron is made up of d and u charge. Okay, so whenever the nucleons come very close to each other, so these charges will be effective, and there will be a force of repulsive between the two nucleons when the distance between the two nucleons is nearly 0.5 femtometers. Okay, so the two nucleons cannot come closer than this distance 0.5 femtometer. Okay, so the range of the nuclear forces is from 0.5 femtometers to the 2 femtometers. Okay, and beyond this, so this is a nuclear force, and beyond this there will be a coulombic force. Okay, so when the nucleus, so this coulombic force has an infinite range. Okay, so the nuclear forces are the short range forces which play or which are effective in this range 0.5 to 2 femtometers. So this coulombic force has an infinite range. Whenever the radius of the nucleus is say greater than 4 femtometer, or say 5 femtometer, then there will be imbalance between the nuclear forces and the Coulombic forces, and at that time, or these type of a nuclei which are unstable, they try to attain the stability by some decaying process of the alpha particles, beta particles, or some gamma particles. So let me tell you few examples of what is the value of this R for the different mass numbers. So we know the formula for R is equal to R naught A raised to 1 by 3. This is a formula for the nuclear radius. So this R naught is 1.2 femtometer, which is the core radius, which is fixed for the all the nuclei. So this is R naught, and above that these nucleons are distributed. Okay, so the size of the core will remain fixed, which is 1.2 femtometer, and as the A goes on increasing, the size of nucleus will go on increasing like this. Okay, so suppose for A is equal to 150, if I take it as a 150 raised to 1 by 3, so it will be nearly 1.2 into something like 5.2, and the answer will be 6.2 femtometers. Okay, so it is likely to seen that with A greater than 150, the Q value is positive. Q value is positive, and the nucleus becomes unstable, and there is imbalance between the nuclear force and the Coulombic force. Now what is this Q value? Suppose I have any reaction written over here. Suppose this is X, now this is Z, this is A, this is a mass number, and this is giving out some Z minus 2, Y, A minus 4, plus 2He4, and plus some amount of energy. Now suppose actually this is a general equation for the alpha decay. Suppose I have taken any element with the atomic number Z and mass number A, and if this element is unstable and if it is giving out some alpha decay, alpha particle is nothing but the helium particle with atomic number 2 and mass number 4. So the mass number of the X element will reduce by 4, A minus 4, and the atomic number will reduce by 2, therefore I have written it Z minus 2, and some amount of heat is evolved in this reaction. Okay, as this heat is evolved, we can say that the Q value of the reaction is positive. Okay, there are some reactions for which you need to supply some amount of energy. In that case, the Q value is negative. But the reactions in which heat is evolved, okay, energy is given out, okay, such type of reactions are called as a sort of exothermic reaction in which the heat is given out. So for the nuclei with a mass number A is greater than 150, the Q value is a positive. And for the alpha decay, typically there are few nucleons, say A nearly greater than or equal to 210. These shows the alpha decay. Now let me draw the graph of this Q value with this mass number. So this Q value goes on increasing with an increase in mass number. There is one more important law related to the alpha decay, which we'll call it as a Geiger-Nuttall law. So this is a graph of a T1 half versus the Q value of the reaction. This is log of T1 half. So I'll write it here, log of T1 half, and its values ranges from minus 10 to plus 10, and the graph has a nature like this. And here is some, this A greater than 150, the Q values are positive. This point is over here somewhere. T1 half ranges from 9 years to 10 raised to minus 7 seconds, and we can see that there is a larger range of the half-life period of the radioactive material, whereas the Q value changes only from 4 to 9 MeV. This log of T1 half, or the half lifetime period, is very much sensitive to this Q value of the nuclear reaction. Now let us take an example of the alpha decay. Suppose this is a uranium 92-238, which is given out with a thorium 90-234, and plus this 2He4, and some amount of heat will be given out. Okay, so the Gamows one scientist who satisfactorily explained the alpha decay process. So let me write here alpha decay by Gamows theory. So what this Gamows did, he considered the nucleus, okay, and he presumed that this alpha particle is already generated inside the nucleus, as the nuclei with a greater than 200 or 210, they are giving out the alpha particles. So large number of nucleons are available over here, and to attain the stability, this nuclei is giving out the alpha particle. So he assumed that this alpha particle has been already created inside the nucleus. Let capital R be the radius of the nucleus, and small r is the distance between the centers of the nuclei and the alpha particle. Now when this alpha particle is inside the nucleus, it is only under the influence of the nuclear force, and as soon as it come out of this nucleus, then it is governed, or it is under the influence of the Coulombic force. Now we can write the situation like for R greater than R. So this is the case where this alpha particle is outside the nucleus, and it is under the influence of Coulombic repulsive force. And for this R less than R, it's under the influence of the nuclear attractive force. So as soon as this alpha particle is outside the nucleus, then the potential, or the Coulombic repulsive potential, can be given out by the equation Z minus 2 into E be the charge into 2E upon 4 pi epsilon. So let me call it as a another R like this. So the Coulombic repulsion between any two charged particles can be calculated by using the equation Q1 Q2 upon 4 pi epsilon naught R, where Q1 and Q2 are the charges on the charged particles, and R is the distance between them. Okay, so I can write this Q1 Q2 upon 4 pi epsilon naught R, where R is the distance between the two charges and Q1 Q2 is the charge on two charges. So Q1 is nothing but Z minus 2 into E, and the another charge is alpha particle whose electronic charge is 2 into E, so divided by 4 pi epsilon naught R, but where the R is the distance between the alpha particle and the center of the alpha particle and the nucleus. So we can write this R as R of this uranium plus this R of this He, and which we can calculate again. So this R of U is equal to 1.2 into 238 raised to 1 by 3. This is from the relation that R is equal to R naught A raised to 1 by 3. where this r naught is fixed as 1.2, and this comes out to be nearly 7.3 femtometers. And this r of He can be given by 1.2 into 4 raised to 1/3 is the mass number, and it will nearly come around 1.89 femtometers. Okay, so addition of these will give me the value of this r as give me some r 9.19 femtometer. Okay, now putting the value of this into this equation, we can get, so this Vc is equal to 2 into z minus 2 bracket square upon 4 pi epsilon naught. So this r like this, so we can write it 2 into 90 upon 9.19, and this term is square upon 4 pi epsilon naught. So this term is nothing but 1.44 and multiplied by these two, so this will come nearly around 19.7, and therefore we are going to get 28 MeVs. Coulombic repulsive potential at this point is nearly 28 MeV. Of course it will change with this A mass number, but for this uranium, so this nearly comes out to be 28, rough calculation, so this will nearly come out to be 28 MeV. Now we have seen that this alpha particle energy is ranging from 4 MeV to 9 MeV, whereas the Coulombic barrier potential is nearly of 28 MeV. Okay, so this causes a puzzle how the particle with a kinetic energy of 4 to 9 MeV is coming out of the barrier potential of 28 MeV. And here comes the help from the quantum mechanics, which allows tunneling of a particle having the small kinetic energy through the barrier height of the higher potential. Okay, and this effect is called as a quantum tunneling effect. V effective nuclear attractive potential, which is shown as a depth of the square well potential of nearly 36 MeV typically. Okay, and this is a Coulombic repulsive potential, which is a kind of a central force field. It is decaying with a distance r. Okay, now we are saying that this height of the barrier potential is nearly 28 MeV. Of course it changes with the A. Okay, but that uranium it will nearly come around the 28 MeV. And now we are saying that the alpha particles which are coming out of this nuclei have the kinetic energy of nearly 4 MeV. So 4 MeV to 10 MeV. Okay, so these are the alpha particle energy. So this is the alpha particle energy which is coming out, and we can see that the height of the barrier potential is much higher for the alpha particle to come out, but still it is coming out of this barrier potential of the 28 MeV, which is explained with the help of a quantum tunneling effect. As in quantum mechanics, we say that the particle has a wave nature. Okay, so if there is a wave nature is there, so the particle with the wave nature of this can penetrate through the barrier potential and it may go out. Okay, so this is the due to the blessings of the quantum mechanics or the quantum tunneling effect, we can explain the jumping of the lower energy alpha particle through the much higher barrier potential of the Coulombic repulsive force. And this quantum tunneling effect was applied to the alpha decay successfully by this Gamows. So it is called as a Gamows theory of the alpha decay. So quantum tunneling effect says that the probability of any such a quantum tunneling effect is P is equal to e raised to minus 2 gamma into d, where this d is the this depth of this square wave barrier potential, and this, if this particle is having the kinetic energy of E and V naught is the height of the potential barrier, then this gamma is given by square root of 2m upon h cross square V naught minus E. Gamows have calculated the probability of the quantum tunneling of the alpha particle, and which was given by P is equal to e raised to minus 2g. Okay, and in our case this g is given by square root of, this is much more lengthier equation, 2m upon h cross square z1 z2 e square upon 4 pi epsilon naught. So this is r from b into 1 upon r minus 1 upon b into this dr. So what are this r and b? So I'm enlarging this portion of the figure, or I'll just draw it once again. Okay, so when the alpha particle is moving in this portion, so this portion is supposed to be divided into small rectangles, and we are taking integration of all these parts like this. So this point we call it as R, and this point we call it as B. So we have integrating, as we know the equation for the square wave potential, we are applying it, or we are dividing this into the small squares or the rectangles, and we are taking integration of all this, and therefore we are getting the equation quantum tunneling of the alpha particle. Along with this equation, we can also say that if there is a even nuclei, so which is having the 0 plus as a ground state spin parity, and the first excited state spin parity is also 0 plus, and this middle energy levels are due to the rotational energy levels are there, which we have already seen in a previous lecture. So the energy difference between the excited state and the ground state is given as the kinetic energy for the alpha particle, and we can say that, so there is a more probability of this 0 plus to 0 plus than this 0 plus to 2 plus or 4 plus or 6 plus. The probability of the de-excitation of the nucleus from 0 plus to 0 plus is more. For this, L is equal to 0. For angular momentum for the alpha particle is 0, because due to this L is equal to 0, the height of the potential barrier is lower, and increase in L, the height of the potential barrier will increase by the term L into L plus 1 h cross square upon this 2mr. Okay, so with increase in L, the amount of this angular momentum will change by this L into L plus 1 h cross square upon 2 mr square, which will increase the height of the barrier potential by nearly 0.5 MeV. This also we can calculate. Okay, but the height of the barrier potential is increased by nearly amount of the 0.5 MeV when there is an increase in L. Okay, so there is a more probability of de-excitation from the 0 plus state to the 0 plus state, means the de-excitation is through the lower L values. Just let us summarize the Gamows theory for the alpha decay. Here any unstable nuclei, when it gives out the alpha particle, it is called as the alpha decay. And this excited state nuclei is with a mass number greater than 200, and due to the imbalance between the nuclear force and the Coulombic force, it will give out the alpha particle. And the Gamows first time explained alpha decay with the help of the quantum tunneling effect. By Geiger-Nuttall, we have seen that this alpha particle is having a kinetic energy of nearly 4 to 9 MeV, and the height of the barrier potential, Coulombic barrier potential, was calculated to be nearly 29 MeV, 28 MeV for the typically for this uranium 238. So the quantum mechanics allows us to penetrate this more height with the help of a lower kinetic energy, and this is called as a quantum tunneling effect. And Gamows for the first time applied the quantum tunneling effect to the alpha decay, and they have calculated the probability of the quantum tunneling of this alpha particle through the Coulombic potential of this here barrier potential, and which is given to be by this formula. Probability of the quantum tunneling is given by this equation. And now we can see that there are some so the probability of the alpha particle is more for the higher energy gap between the excited state and the ground state spin parity of the nucleus. We have also seen that the probability of the even nuclei goes on decreasing with a decrease in energy difference between the excited state and the ground state. It decreases with with increase in L, because as L increases, okay, L is the angular momentum of the alpha particle. As the L increases, so the height of the barrier potential will increase of nearly 0.5 m.